In this video, we are going to start a very important topic, which is also known as toppling. In fact, in almost each video, I have said that this topic is very important because the complete rigid body dynamics chapter is very important as far as any medical or engineering entrance exam is concerned, because it has the most large variety of questions which can be intermixed with all other concepts. So this is a very important topic also, which is also called as toppling. Now you can first of all let me demonstrate you that what is toppling. Now you can see that there is a block which is kept on this rough surface, and this is the normal reaction acting on the block in the upward direction, and this is the mg acting on the block in the downward direction. Now as there is no tendency of this block to slide on this surface, therefore there is no friction acting on this block. So this block has no tendency to slip, or it has no tendency to slide over this surface. But if I apply some force on the top of this block, let's suppose F, then this block has tendency of slipping or toppling. But it is given in the situation that if this surface has enough friction which is sufficient to prevent any sliding, so friction would counterbalance this force F. So block will not slide. But you can see that if you are pushing this block in this direction, then this friction is stopping this block to slide, but this block has a tendency to roll about this point. So this block will eventually start to topple about this point, and therefore you can see that if in this position the block is on the verge of toppling, but you can see that this is the point of contact, this one. So it is also called as effective point of contact or pivot point. So if we draw this vertical line which is passing through this point of contact, then you can see that the torque of this force F is in the clockwise direction. So F is trying to topple this body, while the torque of mg acting on this body is in the anti-clockwise direction. So mg is trying to restore the original position of the body, and mg is preventing this body to topple, while F is trying to topple this body. So till the time when the force of mg, this mg, is on the left hand side of this line like that, so a torque of mg would be developed in anti-clockwise sense. But you can see that if I apply this force continuously, and if I topple this block, if I am trying to topple this block, so this mg is shifting towards this line. So in this position, this mg would be acting in the downward direction along with this line, and it is passing through this pivot point. Now if after this point, if I push this block slightly, then the torque of mg would be acting in clockwise sense, and that torque is alone responsible to topple this object. So the major concept of toppling is the fact that the time till which this force mg is not on the right hand side of this vertical line which is passing through the instantaneous pivot point, then this block will have the force F which will try to topple it. But if the torque of F is less than the torque of mg, then this block will not topple. But if we continue to apply this force F on the top point of the block, and this block continues to topple like that, then at the time when this force mg crosses this line and it comes on the right hand side of the line, then there is no requirement of this force F to topple the block, and this mg will alone topple this block in the clockwise direction. So in this case, the torque of mg about this pivot point is 0. But in this case, the torque of mg along this pivot point is in the clockwise sense, while in this case, the torque of mg along this pivot point is in anti-clockwise sense. And let me remind you that toppling is only occurring when this friction is sufficient to balance this F, so that block does not slides. Now there is a very important concept which is called as shifting of normal reaction, which is helpful in calculation of the forces which are required to topple the block. So let's suppose, first of all, there is a block which has this height B and this width A. Now this block has mg acting in the downward direction and normal reaction acting in the upward direction. Now we all know that normal reaction is a contact force as well as the friction is a contact force. So normal reaction depends on the point of contact, and you can imagine that the complete mass of the system is concentrated at this point, center of mass, and therefore you can see that the normal reaction acting on the complete base is equally distributed all over the base. So we can assume that the normal reaction is also concentrated on the bisector line of this block. So the normal reaction is acting at the center of mass in the upward direction, passing through the ground at this point E, where this point E is called as effective point of contact of the block with the ground. So by the name point of contact, I am trying to say that the complete normal reaction acting on the base of the block can be assumed to be concentrated at this point only. But if we are applying some force F on this block on the top point, and the friction is acting, obviously, because friction is sufficient to prevent any sliding. So friction would be equal to the applied force, as it is sufficient to prevent any sliding. This block will not slide, obviously. But if we are applying this force on the top of the block, then this block has a tendency to topple like that, because this force is creating some torque in the clockwise sense. So you can imagine that on this part of the block, which is the right half part of this block, there would be the major contact force that would be acting, and at this point there would be very less contact force which would be acting, because this block has its tendency to slip in the clockwise sense. So I can say that the normal reaction acting on the block, or the normal reaction acting on the base of the block, is now not uniform, and in fact the major value of normal reaction, or the major normal reaction, is acting on this right hand side of this bisector line. So I can concentrate this normal reaction on the right hand side of this line, and hence I can say that the normal reaction has shifted by a distance of x towards the right hand side, or towards the direction in which toppling has a tendency. So toppling has a tendency in clockwise sense, so the normal reaction is shifting in that direction only. So we can say that the effective point of contact is this one. Now it has shifted from this point to this point. And we all know that the normal reaction cannot go outside the block, because this normal reaction will depend on this contact surface of the block with the ground. So it cannot be outside the contact area of the block, because it is the normal reaction acting on the block only. So it has to lie inside the block. So the maximum margin of normal reaction by which it can shift is this length, is the half base length of the block. So normal reaction has a maximum margin to shift like in this direction, which is equal to a by 2. So if we assume that the force is increased and normal reaction is continuously shifting by increasing this force, so the maximum distance by which this normal reaction can shift is this one. So on the limiting case, when this block is just on the verge of toppling, the normal reaction is acting on this edge of the block. So if we increase this force F further, then this block will topple. So what is happening here, that this normal reaction is creating a anti-clockwise torque about the center. You can feel that, and this force is creating a clockwise torque which is toppling this block. So normal reaction is trying to prevent the toppling, and this force is trying to induce the toppling. So you must have heard in the friction chapter that normal reaction and friction are both like brother forces. Brother forces is due to the fact that they are both contact forces, and the friction always acts to prevent any sliding, while the normal reaction is acting to prevent any toppling. So the torque of normal reaction is in the anti-clockwise sense, and the torque of this force F is in the clockwise sense. So the maximum distance by which this normal reaction can shift and by which this normal reaction can prevent this block to topple is this one, a by 2, because the base length is a. So by the maximum distance it would be trying to prevent any toppling. So this is the limiting condition. Now how to calculate this this torque, and how to calculate the limiting condition of toppling. Now I am showing you the three methods to calculate the limiting condition. Now first of all, we know that if the normal reaction is shifted by only a distance of x, while it has a margin to shift by a distance of a by 2, but it is not shifting by a by 2. In fact, it has shifted by a distance x which is less than a by 2, which means that this block will not topple, because till this time also normal reaction has sufficiently enough margin to prevent the block from toppling. So we can say that if normal reaction is not shifted on the edge, then this block will not topple. So if we write down the torque about any point, let's suppose about O. So torque about O will be equal to 0, and obviously the torque about O will be F into B by 2. You can see that the distance of F from this point O is B by 2 in the clockwise direction. F is creating a torque in the clockwise direction. Now the torque of this friction is also in the clockwise sense. You can see that about the center. So the torque of friction would be equal to plus F into B by 2. Now the torque of mg about this point would be 0. So the torque of normal reaction would be n into x in the anti-clockwise sense, like that. So this is equal to, this is minus n into x, and that is equal to 0, because net torque is equal to 0. Now we know that this block has no net force acting in the y direction. Therefore the force in the upward direction n is equal to the force in the downward direction, which is mg. So I can say that n is equal to mg. Now obviously the force acting on the block in x-axis is also 0. So the force acting F in the forward direction is equal to the friction acting in the reverse direction. So this is the equation, and hence I can substitute this value. So if F is equal to F, I can say that F into B, because this would be F into B by 2, and this is capital F into B by 2. So the total force will be F into B, and that is equal to n into x, where n is mg, and into x. So this n, or this F, is equal to mgx by b. Now if we wish to find out the maximum value of F for which this block will not topple, F max for which the block will not topple, can be calculated by substituting the value of x max. So x max is equal to a by 2. You can see this maximum distance is a by 2. So F max will be equal to mg a by 2b. So this is the maximum force for which this block will not topple. And this force is also the minimum force which is required to topple the block. This force it is also the minimum force required to topple the block. So this is also the minimum force required to topple the block. Now if we balance the torque about E, so the torque about E would also be 0, because this block is not toppling, and therefore its rotational equilibrium would exist about any of the point. So torque about E would be F into h, where h is this distance from E. You can see that if we extend this F, then this distance would be h. So F into h is the torque of F, and this torque is in the clockwise sense, and the torque of normal reaction will be 0 because it is itself passing through this point E, while the torque of mg would be in the anti-clockwise sense, and it would be mg into x. So minus mg into x, and that would be equal to 0. So this F is equal to mg x by h, and in the previous example I have taken this height h to be b. So if I substitute, if h is equal to b, then F is equal to mgx upon b. So we have already calculated this value of F, that F is equal to mgx upon b. So you can either balance the torque about center of mass, or you can either balance the torque about effective point of contact. Now there is one more method to solve these kind of questions, that you can also calculate the torque by force couple. You can see that this normal reaction is equal to mg, and they are acting in the opposite directions, and you can see that this F is equal to the friction, and they are also acting in the opposite direction. So N and mg are creating a torque couple and F and friction is creating a torque couple. The torque created by N and mg is in the anti-clockwise sense, you can see that, and the torque created by applied force and the friction is in the clockwise sense. So the torque created by the normal reaction and mg and you know that the torque of a force couple is equal to force into distance between both forces. So if I write down the torque of this normal reaction and mg couple, then both are equal to, N is also equal to mg and this is also mg. So torque of this couple is mg into x, and it is in anti-clockwise sense, and torque of the F and friction is F into h, because F is also equal to small f. So it is in clockwise sense, so it is equal to F into h. Now I have equated both these torques because net torque is 0. So the torque of clockwise torque couple and torque of anti-clockwise torque couple would be equal to each other. So this F is equal to mgx by h. So this is the value of F which we have already calculated. So you can find out this value of F by either equating the torque about center of mass, or either equating the torque about effective point of contact, or either equating the torque about force couple. This is the force couple. Okay, so this is the three different methods to find out the value of F for which this block will either topple or not topple. We have already discussed that for what value of X the block will have the limiting condition. So this is the complete explanation of toppling. And the next, in fact, in the same video, we are moving forward for numericals. So let's move forward for the numericals based on toppling.